ZONAIR training. The ZONAIR training consists of 12 chapters. The first chapter is the overview of ZONAIR, and ZONAIR uses a unified high-order subsonic, supersonic, and hypersonic panel methodology as the underlying aerodynamic force generator. It uses an unstructured surface panel scheme compatible to the finite element method. Therefore, one can use the off-the-shelf finite element method pre- and post-processors for panel model generation. And it has a trim module for flexible loads calculation and the aeroheating module for aeroheating analysis. You can map the CFD compute pressure from CFD surface mesh to the ZONAIR model to replace the ZONAIR computed rigid CP. Then ZONAIR can flexibilize this rigid pressure. It has an aerodynamic influence coefficient correction method using wind tunnel measured loads for accurate flexible loads analysis, and the aerodynamic and the loads database for 6 degrees of freedom simulation and the critical loads identification. So if you have a CAD model, you can use the off-the-shelf preprocessor like a Patron and Hypermesh to generate a ZONAIR model. And based on this ZONAIR panel model, ZONAIR generated the ASC, the aerodynamic influence coefficient matrix. Then you can use the wind tunnel measured loads, component loads, to correct the ASC matrix. And using this ASC matrix, you can calculate the aerodynamic pressure distribution and also the force moment coefficients. And meanwhile, if you have wind tunnel measured or CFD computed pressure, you can interpolate those pressure onto the ZONAIR panel model. Meanwhile, if you want to do the flexible loads analysis, you can import the finite element method solution and go to a Spline Module, and you can perform the trim analysis, calculate the flexible loads, and meanwhile satisfy the trim condition. Then you can generate the aerodynamic force and moment coefficients and the component loads. Then one can perform the 6 degrees of freedom simulation and identify the critical loads. And the ZONAIR is based on a high-order paneling scheme. And so at each grid, and ZONAIR place a unit doublet strength, and then on the panel, the doublet strength is a linear distribution, and then we put a constant source on each panel, and because the 4 corner points of each quadrilateral panels may not lie on the same plane. So in order to ensure there's no gap between adjacent panels, so ZONAIR subdivide each quadrilateral panel into 6 triangular panels. So for the continuity of the panel geometry, and then it impose both the Newman boundary condition and Dirichlet boundary condition, and also the Wick condition to solve for the unknown doublet strength and source strength, and from which it can calculate the aerodynamic pressure distribution. And the input data card of ZONAIR is very similar to NASTRAN. Therefore, one can use the NASTRAN preprocessor to generate a ZONAIR input data. And then within each ZONAIR job, you can specify many subcases. And to generate the ZONAIR model, first one discretize the surface by grid points. So this is specified by the grid count, and then we connect the grid points by either triangular panels or quadrilateral panels. The triangular panel is specified by the CTRA3, and the quadrilateral panel is specified by sigma 4. Then, if you have a wing trailing edge, and you can specify C bar along the wing trailing edge, and internally ZONAIR will sweep the C bar to downstream to infinity and form a sheet of wake surface. And also, when the wake impinges on the fuselage, and it creates a discontinuous potential jump across the wake surface, this jump condition is specified by the RBE2 card. And compare the ZONAIR with pan-air paneling schemes. ZONAIR using an unstructured grid scheme, whereas the pan-air uses structured grids. And so if you want to specify define a pan-air panel model, you have to first divide the whole configuration into patches. Within each patches, you have to define an n by n grid. Therefore, this is a structured grid, and ZONAIR use unstructured grid, and so it's very easy to generate a ZONAIR model. And we have validated ZONAIR with the wind tunnel data on many different configurations, and showing here is the pressure along the fuselage on this NACA L51F07 configuration at Mach 0.6, angle technical 4, and the circles are the wind tunnel measured as CP. The solid line are the ZONAIR compute CP. For the supersonic condition, shown here are a generic fighter, and this is a wind tunnel measured CP. This is wind tunnel measured CP on the upper surface of this generic fighter, and at Mach 1.2 and angle tag 4.1 degrees. And this is the lower surface measured by wind tunnel testing. And this is a ZONAIR compute CP on the upper surface. This is ZONAIR compute CP on the lower surface. They are very similar. And also for this generic elevated fighter at Mach 1.2, Mach 2.0, we compare the CL, CM, CD, and between ZONAIR compute result, which is shown by the black solid square, and the open circles are the wind tunnel test. You can see we can get very good agreement. For the hypersonic, and we use the so-called equivalent Mach number transformation to circumvent the super inclined panel problem, and then we use the local pulsating body analogy for flow rotationality effect. And showing here is a so-called compact kinematic energy missile, and which has a band nose. And we compare the ZONAIR solution with the CFL 3D. The first one is at Mach 6, and the body and also the nose is at a -2 degrees angle tag. This is CL, CM, CD. This is the hinge moment about of the nose, and then you can see we can get a very good agreement between ZONAIR and the CFL3D. And this condition is body at 0 angle tag, but nose is at a 2 degree deflection angle, and also we have a good agreement. And this case is the body at a -2 degree angle tag, nose at 0 degree, and this is the CP distribution. The red one is the ZONAIR computed one. The dashed blue line and the solid line are the CFL 3D solutions, and this is the comparison of CL, CM, CC, CD, and CH. And this is a nose at a 4 degree bend angle, the body at a 2 degree bend angle. This is a CP comparison. this is the CD. So at Mach 6.0, this is the hypersonic flow condition. And also it can perform aeroheating analysis. The ZONAIR first based on the inviscid velocity computed by ZONAIR inviscid solver, and then ZONAIR has a Z-stream module which it can compute the streamline on the surface. Then once the streamlines are obtained, the air heating analysis can be performed along each streamline using a two-dimensional boundary layer effect. And then you can compute the heat flux. So showing here is at a cone, 50-degree blunt cone configuration at Mach 10.6, angle attack 5 degrees, and this is the heat flux. The winter test data is shown by the open square. The solid line is the CFL3D solution. The cross is the ZONAIR computed heat flux, and this is the CP contour between ZONAIR and CFL3D. And ZONAIR has a 3D spline module, and it can establish the force and the displacement and force transfer between the structural filament model and the ZONAIR aerodynamic model. So it consists of 4 spline method, and it called thin plate spline, infinite plate spline, and beam spline, and rigid body attachment. These 4 methods jointly generate a spline matrix, and so this spline matrix provides the x, y, and z displacement and slope in 3 dimensions for all aerodynamic grid. And then you can perform a static aeroelastic and trim analysis. So it can generate the static aeroelastic deformation to satisfy the trim condition. Then you can generate the NASTRAN force and moment cost under this trim load, and which one can use this force and moment cost to perform a stress analysis. This trim module uses a modal approach for solving the trim system of the flexible aircraft. The modal approach formulates a reduced order trim system that can be solved with much less computer time than the so-called direct method, and it can deal with both determined and trimmed and over-determined trim system, and the solution of the over-determined trim system are obtained by using an optimization technique which minimizes a user-defined objective function while satisfying a set of a constraint function. And for the symmetric configuration, symmetric about the XZ plane, it requires only the modeling of a half-span model, even for the asymmetric flight conditions. And it can generate the flight loads on both sides of the configuration in terms of NASTRAN force and moment cost. And then one can insert this file back to the finite model to perform stress analysis. And this is showing how ZONAIR can map the CAV compute CP to the ZONAIR panel model. And so this is a CP on X35, Mach number 10, angle attack 5, and computed by CFL3D. Then it can map onto the ZONAIR model, and then ZONAIR can flexibilize this rigid CP to obtain the flexible load. And it has an AIC correction module, and the AIC correction module computes a AIC weighting matrix to modify the ZONAIR computed AIC for accurate flexible loads analysis. It has 2 AIC correction methods. The first one is called the force and moment correction method by Gießen, and another one is called downwash correction method by Pitt and Grumman. The AIC weighting matrix generated by the force and moment correction method is computed by matching the wind tunnel measured section loads, and the downwash correction method is computed by matching the surface pressure that are either measured by the wind tunnel test or computed by CFD. The corrected AIC matrix can be used to provide flexible loads due to structural deformation for trim analysis. And this is the ZONAIR model for various aircraft, the F-16, F-15, Airbus 380, F-18. And then this slide shows the industrial loads analysis procedure. The pressure coefficient on the rigid wind tunnel model at various conditions are measured to obtain the rigid loads. So you have wind tunnel measured loads, and then there's a rigid pressure are mapped onto the aerodynamic model, and accurate mapping of pressure coefficient require a high fidelity panel model that has the same order mode line as the wind tunnel model. So because ZONAIR is high order panel code, it can model the exact aerodynamic outer mode line, just like the CFD. So such a pressure mapping can be accurate performed, and so the accuracy of the map pressure coefficient must be verified by comparing the integrated component loads, such as the wing root bending moment, shear, hinge, with those measured by the wind tunnel test. Then those rigid loads are flexibilized by the static aeroelastic analysis, and then the so-called elastic to rigid ratios of the component loads at all flight conditions are incorporated on an aerodynamic database. So if you have a wind tunnel measured load, and then you have a finite element model, then we can perform a static aeroelastic analysis to compute the E over R. And showing this side is the conventional flight dynamic model. So you give a pilot input, and going through the flight control law, the flight control law deflect the control surface through the actuator. Then based on the current airframe states, and then you can go into the nonlinear aerodynamic and the propulsion database to interpolate the aerodynamic forces and moments. But this aerodynamic database usually is measured by the wind tunnel test on the rigid aircraft. Therefore, we have to give the elastic to rigid ratio to flexibilize those aerodynamic forces and moments, and then this force and moment become the right hand side of the nonlinear six-stop solver, and meanwhile you give an aircraft mass and the inertia, then you can calculate the aircraft states at one time step. Then this one we will feedback to the sensor to calculate the airframe states at the next time step. But based on the aircraft states, airframe states, and and we have a nonlinear loads database like wing root bending and shear, also are measured by the wind tunnel. Then ZONAIR can flexibilize this rigid component loads. Then it can calculate the loads and the pressure, and then you can calculate the airframe stress. So the flight dynamic simulation using the aerodynamic database is conducted to search for the critical loads condition. The distributed flexible load at those critical conditions are used for stress engineers for structural sizing design. And how ZONAIR perform the static aeroelastic analysis? And this is the equation shown here. and this is a stiffness matrix. This is AIC matrix computed by ZONAIR. This is spline matrix computed by ZONAIR, and this is the unknown structure deformation. On the right hand side, and FR is the rigid loads, and then one can either use ZONAIR to calculate this rigid loads, or you can replace ZONAIR computed rigid loads by the CFD or computed or winter measured loads. And this is the mass matrix generated by NASTRAN, and this is the aircraft rigid body acceleration. So you can invert this matrix to obtain the structural deformation. Once you solve for the structural deformation, and you can add this is so-called aerodynamic, aeroelastic incremental force, and this is the rigid force. And then you can integrate the total force using a loads integration matrix to give you component loads. Then you can calculate the so-called elastic to rigid ratio, which is the ratio between flexible component loads and rigid component loads. So this is the example for a generic fighter provided by Lockheed, and so a ZONAIR panel model has been generated from the CFD surface mesh provided by Lockheed. NASTRAN model solution also was provided by Lockheed to give us the generous mass and stiffness matrix for flexible loads calculation. And we have the NASTRAN grid for spline, and the two set of trim analysis were performed. One is the rigid loads calculated by ZONAIR, and another one is the rigid loads interpolated from CFD to replace the ZONAIR compute rigid loads. And the NASTRAN static analysis was performed using the NASTRAN force and moment cards generated by the ZONAIR trim module. And we can compare the component loads, the shear, bending, moment, and torsion, and the elastic to rigid ratio of CL alpha and CM alpha. So for a given CFD surface mesh, and we can generate a ZONAIR panel model, and then we impose the specify the flow through condition on the inlet panels, and this a comparison between the rigid loads computed by CFD and computed by ZONAIR at Mach 0.9 and angle attack 0 degrees. So you can see at Mach 0.9, the CFD compute shock strength is much stronger than ZONAIR CP. Okay, therefore, because ZONAIR cannot capture the transonic shock. However, if we interpolate the CFD CP distribution onto the ZONAIR model, you can see those two sets of CP distribution are almost identical. That implies this mapping procedure is very accurate. This is because the ZONAIR panel model and CFD surface mesh almost share the same outer monoline, and therefore the mapping is very easy. So then we generate a spline. Then all the structure mode are splined from the NASTRAN model to the ZONAIR panel model. Then we can calculate the CL alpha, the E over R of the CL alpha, E over R of the CM alpha at different dynamic pressure. And if we use ZONAIR, and this is E over R of CL alpha, this is E over R of CM alpha, then if we use the ZONAIR CFD computed CP to replace ZONAIR computed CP, then we flexibilize the CFD computed rigid CP. Then this is the EOR of the CM alpha, and this is the EOR of CM alpha, and this the horizontal tail generate the CL, and this is CM per horizontal tail deflection angle. Then we can perform a trim analysis. The trim condition is at Mach 0.9 sea level at a 9G pull up condition, and then the trim equation requires to satisfy the lift equal to 9G and pitching moment is 0 about the CG, and then you can see this the rigid load computed by ZONAIR. Then ZONAIR compute the flexible trim solution, and then this is a rigid load computed by ZONAIR. Is replaced by the CFD. Then ZONAIR flexibilize this rigid loads to compute the trim solution, and then you can see the difference. And then we can compute the section loads. This is a sectional shear force along the wingspan. This is a bending moment along the wingspan. This is torsion moment about the collar core along the span. And then we can. This one is ZONAIR compute rigid shear force by the blue triangle, and then if we use ZONAIR to calculate the flexible one, and it's showing by the red. Now the bottom one is the ZONAIR compute rigid CP is replaced by the CFD computer one, and so the blue triangle at this time is actually the CFD computed CP map on ZONAIR, and ZONAIR calculate the sectional loads, and the red one is ZONAIR further flexibilize the rigid CP to calculate the component loads. So this is the difference. And at the end, the trim module of ZONAIR can generate a force moment cost, the NASTRAN force moment cost, and the user can insert this file into the NASTRAN input deck for a detailed stress analysis. So this is the stress analysis, and because ZONAIR is allowed to use the so-called thin wing model, and the thickness effect is simulated by the source sheet, and then we put the doublet on a thin wing, which is a flat plate. And so if you want to add the underwing store to a ZONAIR model, you can use the thin wing to model the pylons. Then you can model the fins of the missile by the thin wing model. The thin wing model is called CL7.